Kia ora and welcome to this video on question 4 of the 2020 Scholl Calc exam. This question's all set in the context of integration and differentiation. The first question involves a proof that's pretty mean for a part A of a question. The proof has got a little bit of a trick halfway through that if you've seen it you might have a head start. If you haven't seen it, it makes it quite tricky, and it's unlikely that they'll ask this again in the near future. If you've seen it before, you can regurgitate it. 4b involves integration by parts, which is beyond NCA level 3, but only just slightly, and it comes up quite often. And then 4c involves implicit differentiation, which is an application of the chain rule, not an NCA level 3, but again, just outside of it. So these questions here are quite common, or involve common techniques. Okay, so question 4a. The first thing is, what does first principles actually mean? In terms of calculus, first principles is this formula. It says that if you have, off to a bad start trying to write with a highlighter, if you have some function, if you have a function u, then its derivative can be found using this limit. And if you haven't seen this before, and you're in a calculus class, I cry a little inside. It's not an NCA anymore, but it's actually where calculus came from. So just to draw you a little graph of the situation. So if we had some random graph here, y equals u of x, and we wanted to find the slope at a particular point, because calculus, and when we differentiate, it's all about slope, right? How things are changing. So if I say this point is x, and I want the slope at that point, we need to find its derivative at that point. However, before you got to calculus, you only knew how to find gradients between 2 points. So if I call this point here x plus h, so the difference between the x values is some value h, and this function value here is u of x, and this function value here is u of x plus h. And when we found gradients between 2 points, it was rise over run. The rise over run gives us the stuff that we've got up there. The rise is the difference between the y values, and we want h to be limited to 0, because we want those 2 points to converge, or at least this point to head towards the first point we started with, and that will be the case if h approaches 0. Okay, so limits are all about what happens as something approaches something, and if we make h really small, then this fraction here approaches the gradient. Okay, if you want more on the definition of the derivative and differentiation by first principles, then you should look it up. But that's what we're working with. Okay, what we're asked to do here is actually to prove the product rule. It says the derivative of a product is the derivative of one function times the other, plus the derivative of the other function times the first one. So we're asked to prove the product rule here. So we can start off with left-hand side. When we've got a proof, this is a good way of setting it out. Left-hand side is the derivative. d dx means the derivative of f of x times g of x. Now we can't use the product rule in this because we're trying to prove it, and so the only thing we can use is first principles. We go, okay, well, we've got some function which is f times g. The derivative will be, the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x. I've just got rid of the time symbols, all divided by h. Okay, and with this, if you've seen these things before, you can't make h 0 because you get division by 0. So this is where the little sneaky trick comes in, and like I said, if you'd seen the proof before, you would kind of know this or expect this next point. We'll reflect on it at the end. But what you do is you add 0 to the numerator. So at the moment, we've got f of x plus h, g of x plus h. And what I'm going to do is take away f of x plus h times g of x, and then add it back in again. And there is a reason why I've done this. That right-hand side that we're aiming for has two terms in it. It has a derivative in the first part and has a derivative in the second part. So I actually want to turn it into 4 terms. So play around a little bit with this. You can see that those first 2 terms in the numerator actually factor out an f of x plus h. And then the remaining bracket has g of x plus h minus g of x in it, which looks very similar to the derivative of g. And then the last 2 terms have a common factor of g of x and this is where you have to understand properties of limits. If you have 2 functions and they multiply together, their limits, as it approaches some point, will be the product of the limits. So, and also for sums. If I have a function and I know its limit, and have another function, its limit, the limits will add. So what I can do is write it seems really silly to do this, but this is what it comes out to be. I'll leave the h with that one because I want the derivative term there. I'll stuff that one up. And then the other term, I want the h with the first stuff, then multiplied by the limit as h goes to 0 of g of x. Okay, now we can't make h equal 0 in the terms that have got fractions in them, but we don't need to because we know that this whole thing here is g dash using the first principles. So that is g dash. This bit here is f dash. Limit as h goes to 0 of f of x plus h. Well, I can make h 0 there and I just get f of x. And then this last term, the limit as h approaches 0 of g of x. Well, g of x doesn't depend on h, so it's just going to be g of x always. Okay, and that's the proof done. Because you've got the product rule there, the function times the derivative of g of x, and then the derivative of f of x is there as well. Now that problem there was hard, like I said at the start. But if you got stuck on it, you could actually start on the right-hand side. And if you used first principles on the right-hand side, which is that one and that one, you'd be on the right track. But then you'd need to, need to know that you could put this stuff back inside the limit there, and so it's not an easy question. Alrighty. Fortunately, the rest of this question is actually not too bad. Okay, so let's look at 4b. Using this result, which is the integration by parts, and the cool thing is integration by parts actually just comes from rearranging the product rule. If you're unsure about that, just Google it. It's quite a common proof. If you rearrange the product rule, you get this integration by parts formula. And the key thing with integration by parts is you turn an integral that you either can't do or something that's a bit tricky into something that's a little bit easier. Okay, so we want, when we take the function g and differentiate it, we want that right-hand side integral to be easier than the one we started with. Now, this is not a very good example of what I mean by that, because this question is one that actually doesn't get any easier. The integral stays equally as difficult, and we just do it twice. We'll talk about that in a sec. Okay, so let's find this integral. I'll start it on a new page. Integral e to the minus x times cosine x. And we need to choose for the integration by parts. So here, what do we make the f dash and what do we make the g? So I'll just write down this integration by parts formula. Integral of f dash g dx is fg minus the integral of fg dash dx. So what do we choose as the f dash and the g? It actually doesn't matter for this particular problem, but let's make this here the f dash, and let's make this the g. If f dash is e to the minus x, then f is its antiderivative, which is minus e to the minus x, and g dash is the derivative of cosine, which is equal to minus sine of x. Notice in integration by parts, we don't need a plus c when we write down that f function. Okay, so this integral equals f times g, so minus e to the negative x times cos x, minus the integral of fg dash, which is negative e to the minus x, times negative sine of x dx. Now I've got a whole heap of negatives going on here, so I've got a minus, 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 so I'm going to keep that as a minus. And like I was saying, it didn't really matter what f dash and g were in the original integral, because the exponential function, or e to the power of something, just stays equally as difficult. And the cosine switched to sine, but if we do it again, it's going to go back to cosine, and it feels like you've actually not made any progress. However, this is a special example of integration by parts, as you're going to see in a sec. So we're going to do it again. This time I'm going to make this one f dash and this one g. I don't want to go back to where I started, so I'll keep the same format. Be real careful of your minuses here. Minus, okay, this next integral, we've got an fg. F is, I haven't written it down, but it's minus e to the minus x again. G is sine of x, minus the integral f, negative e to the minus x, and g dash, which is cosine. Again, when I do these integrals, I don't need the plus c's in them. That will come at the end. Okay, now it looks like we've made no progress because we've appeared kind of where we started, but if I simplify this out, and that last one is a minus, minus, minus. Okay, so that's what I've got. And I've appeared with an integral on the right hand side, which actually was the same as the integral I started with. So what we do in a case like this is we go, let I be the integral we were trying to find. I is equal to e to the minus x cos x plus e to the minus x sine x minus the integral we started with. And if we put that on the other side, it's going to be 2i, and then I can divide by 2. I like to call this like a loop. It loops around. So we've got, there's also a common factor of e to the minus x in here. all of that divided by 2. I do also need a plus c somewhere, so I'll put it there. And that there is the antiderivative that we wanted. You can also check that by differentiating it. You'd need the product rule, but if you differentiate that, you'll find that it comes back to where you started with. Okay, the second part of the question asked us to find the area between the curve, which we've just integrated, and the x-axis between 0 and 2 pi. It's a really easy mistake to make in this question, that you just integrate between 0 and 2 pi. But with any function where you're trying to find its area, you must, absolutely must, look at the graph. You've got a graphics calculator, but here I'm just going to use Desmos because it's easier to display it as I make this video. And if I have a look at what this function actually looks like, hopefully that, yep, accepts it as e. If anyone was wondering what e is, that's just that number there. It's kind of like pi, it's a bit special. Okay, and Desmos on here is a little bit clunky. Nope, where is my power? Oh, there it is, it's right in front of me. E to the minus x, and then times by cos x. Alrighty, zoom in, and we're going between 0 and 2 pi. Oh dear, we have x-intercepts. Pi over 2 and 3 pi over 2, and there's 2 pi. Oh, that's not even 2 pi. Where is 2 pi? Oh, that's a maximum. That's not an issue. But we've got two x-intercepts to actually factor in, 3 pi over 2 and pi over 2, where the area is above, then below, then above. And if we didn't realise that, our answer is going to be very slightly out from the real answer, because the area below and above is tiny, but there'll be a bit of cancellation. Okay, so we get rid of that. So if we just integrate from 0 to 2 pi, we're going to get the wrong answer. So name that part I. Okay, so the area is equal to the integral between 0 and pi over 2. I'm just going to write f of x. Can't be bothered writing out that thing again. That was above, then it went below. So it's plus the absolute value of the integral between pi over 2, 3 pi over 2. Should really be putting dx's here. Oh, we're having a bit of a technology mare. Integral of f of x dx plus the absolute value between pi over 2 and 3 pi over 2. And then plus that extra little bit at the end of it, 3 pi over 2 up to 2 pi. Now if you're wondering, how do I find those x-intercepts without technology? Well, I use Desmos, but you could also use your graphics calculator. The function was e to the minus x multiplied by cos x, and we just need to find out where it equals 0. Now, the first factor, e to the minus x, is always positive, which means that we just need to consider where does cosine x equal 0. And a quick sketch of a cosine graph, it equals 0 there at pi over 2, and again at 3 pi over 2. So that's the roots of the original function. Okay, now fortunately we've already found this integral. We don't need a plus c when we're dealing with definite integrals. The c's would just cancel. But what we need to do is evaluate this antiderivative, e to the minus x all over 2 sine x minus cos x between pi over 2 and 0. I know the next part's going to be negative, so I could just minus it. Minusing a negative is adding the area. Between pi pi over 2 and 3 pi over 2, and then the last one plus the last area. Between 3 pi over 2 and 2 pi. And to be honest, I can't be bothered substituting these things in. I would just cheat on the calculator and do the integral. But just had to break it up into 3 parts and get my answer. If the question asked for exact areas, then I would need to do the substitution. Let's see. Oh, it did say find the exact form. Darn it. Okay, so when I substitute in the top limit pi over 2, sine of pi over 2 is 1, cos of pi over 2 is 0. So that first term becomes e to the minus pi over 2 over 2 minus the bottom limit, which is 0. Sub that in, I get e to the 0 is 1. So half sine of 0 is 0, cos of 0 is 1. But it's a minus 1 there. Okay, so if I sub in 0 into there, it's a minus. It's got a minus in front of it. Okay, and then we've got to take away the next term. If I sub in 3 pi over 2 into the sine function, I get negative 1. So it's minus e to the minus 3 pi over 2 over 2 times negative 1. And if I sub in pi over 2, it's going to be minus e to the minus pi over 2 all over 2. Sine of pi over 2 is... Oh, I've already stuffed something up, haven't I? Told me I didn't want to do this one. That's the first term. The second term's got 3 pi over 2 and pi over 2, so none of the terms disappear. E to the minus 3 pi over 2 over 2. Sine of 3 pi over 2 is negative 1. Cos 3 pi over 2 is... Oh, what am I, mate? Cos 3 pi over 2 is 0, so that's cool. Take away the next term, which is pi over 2, e to the minus pi over 2 over 2. Sine of pi over 2 is 1, cos pi over 2 is 0. Sweet. And then the last term plus, just chuck in 2 pi. Sine of 2 pi is 0, cos of 2 pi is 1. So it's minus 1. Take away the bottom limit. Sine of 3 pi over 2 is negative 1. Cos of 3 pi over 2 is 0. Okay, what have we got here? We've got two terms that involve e to the minus pi over 2, and they're both adding. So we've got e to the minus pi over 2. They've both got a half under them, but there's two of them. In that first term, we've got plus a half. And then we've got two terms that have got e to the minus 3 pi over 2 in them. One of them is a minus and the other's no, they're both pluses. So we've got plus e to the minus 3 pi over 2. And then that last term's e to the minus 2 pi. The minus is minus a half e to the minus 2 pi. And I believe that that is the area. I'm just going to consult the schedule. Hallelujah. Of which we can confirm on our calculator and check that the decimals are equivalent. That's a really stink question. I bet you heaps of people stuffed up the first line by integrating from 0 to 2 pi though. Alrighty, the third question, third part of it. Question 4 and 5 are usually the trickier questions in the exam, the ones that sort out the best students. Part C, we've got a function defined implicitly by this relation. Evaluate the second derivative. Okay, xy plus e to the y. What was the rest of it? Equals 2x plus 1. Okay, so for those of you who have never seen implicit differentiation and how it works, basically, implicit differentiation allows you to differentiate equations without rearranging them. And all you need to know to do this is if you have some expression, for example, y squared, where the dependent variable is there, we need to think of y as f of x all squared. Okay, y is some function of x, we just don't need to find it. And in some cases you can't actually find it because the equation won't rearrange. Like the one we've got here. If we want to make y the subject of it, we've got a bit of an issue because there's a y there and there's an e to the y term. So we can't actually make y the subject. We could make x the subject though. That's one way of doing this actually. We could make x the subject. I'm going off on a bit of a tangent here. Excuse the calculus pun, but if we make x the tangent, sorry, x the subject, I could then find dx dy. Then I flip it upside down to get dy dx. But then I have to find the second derivative, so no, I can't be bothered doing that way. It's going to be messy. Implicit differentiation allows you to differentiate without doing any rearranging. And all you need to understand is this thing here, this y squared thing, we could write as f of x squared. And how do you differentiate some function squared? Well, the 2 comes down the front, 2 times the function to the power of 1, and then you always multiply by the inner derivative, which would be f dash of x. If we wrote this with y's, we'd write 2y times dy dx. Okay, so basically if you want to differentiate something that's got a y in it, you diff like normal, so y squared becomes 2y, but then you put a dy dx afterwards. If you want to learn more about implicit differentiation, I suggest you look it up because it's really common in scholarship. Okay, so the first term's not nice. X, y, you have to realize it's a product. It's like f times g. So if I want to diff this, I think of this as my f and this is my g, then f dash will be 1, but g dash will be 1 times dy dx, okay, because we're diffing with respect to x. The second term, e to the y, well, I can diff that as long as I put a dy dx factor on it. So doing this, the first one, x times y, I need to diff the x, so I get 1 multiplied by the second term. Then I diff the second term, dy dx times the first term, that's the product rule. And then e to the y diffs to the same thing, but just times dy dx. The right hand side, the 2x diffs to 2, and the 1 disappears. Now at this point we can make dy dx the subject by grouping the terms that have got dy dx in them, and then moving everything else to the other side. So it's just a 1y at the front that I've moved to the other side, 2 minus y, and then I've got dy dx equals 2 minus y over x plus e to the y. That's the first derivative. And the question asked us to diff again. This time we're going to use the quotient rule. So if I call this dude my f, this dude my g, then f dash is going to be minus dy dx. The 2 disappears and the minus y becomes negative 1 times dy dx. And here the denominator g dash, x will differentiate to 1, and e to the y is e to the y dy dx. Okay, and I use the quotient rule. So second derivative, diff the top times the bottom, so minus dy dx times the bottom, take away diff the bottom times the top, all over the bottom thing squared. Yes, that's the quotient rule. Okay, and then the last step is, what did it ask us for? It asked us for the value of that when x was 0. Okay, so first up, when x is 0, if I make x equals 0 in the original problem, I end up getting e to the y equals 1. so y is equal to 0 as well. So I'm going to sub in 0 and 0 in for all of the x's and y's. That first term here asks us for dy dx, and there's also a dy dx in there. We can use the formula, the line above it, to find out this formula here. We sub in y equals 0 and x equals 0, and we get at x equals 0, y equals 0, dy dx equals 2, and d squared y over dx squared therefore equals minus 2 times 1 minus, I'm subbing in zeros for x and y, 1, e to the 0 is 1, dy dx is 2, 2 minus 1, oopsies, no it wasn't 2 minus 1, it's 2 minus 0, all over 1 squared. Okay, and if you work that out, comes out to be minus 8. Okay, it wasn't too bad, but you needed to know implicit differentiation to be able to do it. Now, that's the question done, but while I've got you, if you want to watch for another 5 or so minutes, I'm going to show you a different technique that you could use for differentiating messy stuff, and that's called using logs. Differentiation using logs. We'll start off with the product rule. If you have a function y equals f times g, for example, we know that there's a formula that enables us to diff that. Okay, we know that it's y dash is f dash g plus g dash f. Okay, we know that exists. However, logs are quite useful because logs turn things from products into sums. If I log both sides of this expression, log of y, and I use the natural log because I know it's derivative, any log would have done. Okay, log both sides. Using log rules, that becomes log of f plus log of g. Now if I use implicit differentiation on this, the left hand side diffs to 1 over y times y dash, and the right hand side differentiates to 1 over f times f dash plus 1 over g times g dash. That's all implicit differentiation, and then therefore y dash, the derivative we wanted to find, is equal to y. I need to bring this y up to the top right of the other side. So at the bottom left, I need to move it to the top right. Okay, so we get that, and then remember that y was equal to f times g. So we've got fg times f dash over f plus g dash over g, which doesn't look like the product rule, but see that the first term, the f's cancel, and you get f dash g. In the second term, the g's cancel, so you get g dash f. That's pretty neat, right? And I didn't have to use any product rule, I just diffed implicitly. Now I'm thinking like, how could that help in the problem we just finished? Well, there is a product there, x, y, so if I wanted to turn that into a sum, I could log it, but the rest of the problem is a sum, so using logs there wouldn't be helpful. However, if you've got a function, and there's been a few in past scholarship exams, which involves powers, multiples, and powers, multiplications, and divisions, using logs turns the problem into something a bit simpler. And on that note, I hope I've taught you some stuff that you didn't know, and we'll see you in the next video.